Let's review paper 2 for the 2019 May IB Physics SL exam, and this is version 2. There's a single fly in this room buzzing all around. I don't know if you can hear it, but I can. So a student strikes a tennis ball. It's initially at rest and leaves the racket at a speed of 64 meters per second. The ball is a mass of, okay, all that stuff. So now calculate the average force exerted by the racket on the ball. This gives time, speed, and mass. That makes me think momentum. Why does time make me think momentum? Well, because momentum, we learn about momentum from force. Time graphs, we learn about energy, however, work from force position graphs. So time, speed, and mass all make me think of momentum. So I use force is equal to change in momentum over change in time. And then, well, the change in momentum is change in mv, but the m doesn't change in this case. It's just the v that changes. So I just apply the delta to the v, and then you just plug and chug. So 58 grams, or 0.058 kilograms, times 64 meters per second, divided by 25 times 10 negative 3 milliseconds. Very important. You get 150 newtons. Now the average power delivered to the ball during the impact. Well, I thought of it in terms of power is equal to work divided by time. So net work, is change in kinetic energy. So if I can find the change in kinetic energy and I know the time, I'm good. They gave me the time. I can find the change in kinetic energy because the ball started from rest. And that's also why this was just 64. The ball starts from rest. Initially at rest. So then 1/2 mv squared divided by t. I just brought that 2 and the 1/2 down there. We get our mass, 0.058. I know that looks ugly. I started right 0.58. And then times 64 squared divided by the time of impact. Again, we get 4.8 kilowatts. Another way you could do this is power is equal to force times velocity. However, the force is variable and the velocity is variable in this problem. So you'd have to do average force and average velocity, which I don't like that method. It is in the scoring guide, though, if you want to look at the scoring guide to learn more about that. If you have questions, you can ask me later. So now we have more information about the situation. The student strikes the ball at an angle of 7 degrees down from a certain height, certain distance from the net, with a net height of a certain value. So now we want to calculate the time it takes the tennis ball to reach the net. Well, the net is a horizontal distance away. So we're just going to take the horizontal motion. And that horizontal motion for an object in projectile motion is a constant velocity motion. Vx is a constant, so we can just use equation 1 here, rearrange this to solve for t, and of course Vx is v cosine of theta, because if my velocity is like that, and that's my angle, Vx is going to be adjacent to the angle, and of course v is my hypotenuse, so it's going to be v cosine of theta for Vx. And then I just plug and chug. So it's 11.9 meters away, 64 meters per second, cosine of 7 degrees. Make sure your calculator is in degrees mode. You get 0.19 seconds. Part 2, show that the tennis ball passes over the net. So for that, I just want to look at the, figure out what the y position of the ball is when the ball is at the net. If that y position of the ball is greater than 0.91 meters, then it passes over the net. So for that, well, I know the time, I know the acceleration, and I know the initial y velocity with a little bit of algebra or trigonometry work, and I know the initial y position. So I can use equation 4. So negative 1/2 gt squared minus vy naught t plus vy naught. Plus y naught. Now vy naught is going to be v sine of theta. And just make sure you make it minus, and make sure you do minus for that. Let me plug and chug. G is 9.81. I use 9.81 rather than 9.8 or 10 because that's what's given in the data booklet, though I bet you'd still get credit if you use 10. The time you found in the last part, minus 64 sine 7 times the time again, and this is time squared, of course, plus the initial height's 2.8, we get 1.14 meters, which is greater than the height of the net, so it goes over the net. Now, what if you got the wrong time there, and you do this, and you find, oh no, it doesn't go over the net. Well, I guess that clues you in that you probably did the previous part wrong. Determine the speed of the tennis ball as it strikes the ground. You could do this with kinematics, but I prefer to do this with energy. So the initial energy when the ball leaves the racket is going to be equal to the energy when the ball hits the ground, neglecting drag, which we're doing in this problem. When the ball is hit by the racket, we've got gravitational potential energy and kinetic energy. When it hits the ground, we've just got kinetic energy, assuming we set the ground as h equals 0. You don't have to, but that's the best thing to do in this context. It simplifies things. So mgh plus 1/2 mv0 squared is equal to 1/2 mvf squared. M cancels out. Multiply both sides by 2 and take a square to solve for vf. Plug and chug your 2, your g, your h, and your v0. And then you get 64.4 meters per second. Now this is, as written, this is technically a 2 sig fig problem, I think. So that would leave you with just 64. That's the same speed at which you launch the ball. So I put the 64.4 in there just to differentiate this speed from that speed, because the speed doesn't change very much as it falls 2.8 meters in this case, because the initial speed was so high. And that's what IB did as well. Did you just see the fly? And that's what IB did as well. So it works. Apologies. Okay, so now we're modeling the bounce of the tennis ball to predict the angle it'll have when it leaves the surface of clay or grass. I don't know who plays tennis on, well, I guess our tennis courts surfaces made of clay? Maybe they are. I've never heard of someone playing tennis on grass. So the model assumes during contact with the surface, the ball slides. Okay. The sliding time is the same. Okay. Sliding friction is greater for clay than grass. That makes sense. Clay does seem like it would have a higher coefficient of friction with just about any given material than grass. The normal reaction, normal reaction force, that's just the upward force. Upward, not because normal force is always upward. Upward because normal means perpendicular, which means perpendicular to the surface. The surface is horizontal. Normal force is upward. And that force is the same for both. Predict for the student's model without calculation whether theta is greater for a clay surface or a grass surface. Okay, so it's worth 3 points. So you probably want to say 3 things. So Vx is going to decrease more for clay than it would for grass because you've got a higher coefficient of friction. So you're going to have a smaller Vx final for clay than for grass. However, you're going to have the same Vy final because the vertical force that changes the vertical momentum is the same. Therefore, you're going to end up with a higher angle, a greater rebound angle for clay than for grass. Why? Well, let's say this is my Vx and this is my Vy for grass. And then I do another Vx that's shorter for clay, but the same Vy. You can see that this angle here is greater than that angle there because the Vy component's the same, but the Vx component is smaller. So clay will have a larger angle at which it bounces off the surface. Okay, number 2. A container of volume 3.2 times 10 negative 6 cubic meters filled with helium gas at that pressure, at that temperature. Assume that the sample of helium gas behaves as an ideal gas. That means we can use Pivnert. Okay, so the molar mass of helium is 4 grams per mole. Show that the mass of a helium atom is 6.6 times 10 negative 26. Well, I would say the mass of an atom is going to be equal to the molar mass divided by Avogadro's number, the number of particles in a mole of any given substance. So I do 0.004 because that's the mass in kilograms of a mole of helium. Remember to convert this to kilograms. Divide by Avogadro's number, which you can look up in your data booklet if you forgot it. Avogadro's number right there, 6.02 times 10 to 23. And then you get 6.6 times 10 negative 26 kilograms. Now, if you did leave this in grams, you get an answer in grams, and then you would just convert to kilograms by moving the decimal 3 places. Part B, estimate the average speed of the helium atoms in the container. Well, average kinetic energy, and they write it as E sub K. I write it as capital K for kinetic energy, but they write it as E sub K, and that bar on top means average. So average kinetic energy is equal to 3/2 kb times T. Kb being Boltzmann's constant, which is also in your data booklet if you don't remember its value. And if you don't remember that equation, which maybe you don't, if you go to topic 3, this thermal physics and gases, there it is right there. If you prefer it instead of Boltzmann's constant, you prefer it in terms of R and Avogadro's number, I guess you can use that too. But I like it in this form, so 3/2 kb times T. Now, that's the average kinetic energy, and they want to know the speed. Well, the kinetic energy, normal kinetic energy equation is 1/2 mv squared, and I put the bar on there for average velocity. And then just solve for velocity. These 2's cancel out, so I'm left with a 3 kb. That's a kb. I know it looks kind of ugly. Divide by mass times T under square root, and then plug and chug. 3 Boltzmann's constant, you get that from the data booklet if you don't already remember it. The mass, you got that from before. The temperature, they gave that to you. 1.4 times 10 to the 3 meters per second. Pretty quick. Show that the number of helium atoms in the container is about 4 times 10 to the 20. Okay, so, well, I can use PivNert for that as well, because PivNert includes this n. That's a lowercase n. That is a very small lowercase n. That is the number of moles of substance or of gas in the container. So I can solve for n. It's going to be PV equal over RT. And then, well, the number of particles is going to be, so the number of particles is going to be the number of moles times Avogadro's number. So here I said n is therefore equal to the number of moles times Avogadro's number. Pressure, they gave it to us. Volume, they gave that to us. R is the gas constant. That is also in your data booklet if you forgot it. Right there. T, they gave us T is 320 Kelvin. Always verify the temperatures in Kelvin. Right, so a lot of times they'll give you temperature in Celsius rather than Kelvin. If they give you temperature in Celsius, make sure you add 273. If you want to be really crazy, you can add the 273.15, but that's almost never necessary. And then we multiply by Avogadro's number, which is, of course, in your data booklet, and you get 3.7 times 10 to the 20 atoms, which rounds to 4 times 10 to the 20 atoms. Okay, D, a helium atom has a volume of 4.9 times 10 to the negative 31 cubic meters. Calculate the ratio of the total volume of helium atoms to the volume of helium gas. Okay, well, the total volume of all the helium atoms would be the number of helium atoms times, that's supposed to be a multiplication dot, times the volume of each atom, divided by the volume of the entire container. The volume of the gas is the volume of the entire container, which is given to us at the top. So then we do the number of helium atoms times the volume of each helium atom divided by the volume of the gas, and we get 5.7 times 10 to the negative 5. What is that? That's 57 millionths. That means that only 1/57 millionth of the volume of the container actually contains helium atoms, like it's actually being used up by helium atoms, the space that helium atoms take up. So, coming to part 2, explain using this answer that we just got with reference to the kinetic model why the sample of helium can be assumed to be an ideal gas. Well, in the kinetic model, in order to assume something is an ideal gas, we assume that either, we can say this a couple different ways. We could say that the volume of the particles is negligible compared to the overall volume of the gas, or that each particle is a point particle and therefore has no volume, which would be the same thing as The total volume of the gas, of the particles of the gas is negligible. And this result indicates that, yeah, the volume of the particles of the gas itself, rather the particles themselves of the gas, is indeed negligible compared to the volume of the entire container. Number 3. Okay, so we've got a sound wave going through a piece of metal, and then it's going to enter the air. So we have a particle P in the sheet metal. It performs simple harmonic motion because sound waves are longitudinal, and we're going to have this point P bouncing forward and backwards as the sound wave passes through it. When the displacement of P is 3.2 micrometers, the micro, remember, means millionth. The magnitude of its acceleration is 7.9 meters per second squared. Calculate the magnitude of the acceleration of P when its displacement is 2.3 micrometers. Well, for something in simple harmonic motion, acceleration is proportional to displacement. Why? Well, the force that causes a simple harmonic motion is negative k delta x, or delta x is the displacement, and force is the driving force. The negative means that we have a restoring force. This force is resisting the change in displacement. Now, of course, net force is equal to ma. So we have ma is equal to negative k delta x. That's to the first power. That's to the first power. So if I double the displacement, I double the acceleration. I cut the displacement in a third. I cut the acceleration in a third. Whatever I do to displacement, I also do to acceleration. Now, they are going opposite directions and everything, but we don't care about that for this. We just care about the magnitude. So that's why I don't need any negatives. Now, because these two are proportional to each other, you can do this in multiple ways, but I set it up as two ratios. Acceleration 1 divided by acceleration 2 is equal to displacement 1 divided by displacement 2. Now, I want to know acceleration 2. That's the second acceleration they gave us. So you could have called it acceleration 1, then the algebra maybe would have been a half of a step easier. So then solving for acceleration 2, we get acceleration 2 is equal to acceleration 1 times delta x2 divided by delta x1. Acceleration 1 was 7.9 meters per second squared, they told us. Delta x2 they wanted, which what they gave it to us, is 2.3 micrometers. And then displacement 1 was 3.2 micrometers. Now you might notice that these are micro. Micro means times 10 to the negative 6, but I did not write times 10 to the negative 6. Why? Well, because that would cancel out anyway, because it'd be 1 up here and 1 down here, so I thought I might as well not even write them. It's fine to write them, I just didn't. And we get 5.7 meters per second squared. It's a good thing we got a smaller number, right? A smaller displacement should result in a smaller acceleration. So if you got a larger number, you probably just got these two mixed up. The wave is incident at point Q on the metal air boundary. The wave makes an angle of 54 degrees, so that's an angle of 54 degrees there. Speed of sound in the metal is 6010 or 6010 meters per second. The speed of sound in air is 340 meters per second. Calculate the angle between the normal at Q and the direction of the air wave. Okay, so now this thing is going to come in. This works just like with light. So we can do the same sort of analysis. So we're coming from something that we're moving very, very fast, and now we're going to move slower. So this part of the wave is going to suddenly slow down, and we're going to bend toward the normal. So we're going to be bending toward the normal because we're going from a thing where we're going very fast to a thing where we're going very slow. Now, so to figure out the n value, the way I did it was I said, well, I took V naught to be the speed of sound in air. I took air to be the default rather than the metal. So n is going to be your speed of default divided by the velocity in a particular medium. So in my case, the n for air, the index of refraction for air is 1 because V naught divided by V naught. I took the speed of sound in air as my default. Now in the metal, though, it's going to be, n metal is going to be the speed of sound in air divided by the speed of sound in the metal, which is a very small n value. Could have done the other way, in which case air would have a very large n value of nearly 20. And that works the exact same way for light as well, except instead of the speed of sound in air, your default is the speed of light in a vacuum, c. And that's what goes on top. And then I use Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. So I want to solve for theta 2. So I divided the N2 over. So I have N1 divided by N2 times sine of theta 1. And then I took the arc sine, or inverse sine, to get the theta 2 by itself. Then I just plug and chug. Now, I used the decimal here, and there were more decimals. I used all the decimals that were in my calculator. But I think it would be more elegant to simply write 340 over 6010 right here, and then the 1 down here would just not even be a factor. So I would just write 340 divided by 6010. That's a more elegant looking solution, but it doesn't matter. The sine of 54, because that is the incoming angle, you get 2.6 degrees. Make sure you are in degrees mode. Okay, part C, the frequency of the sound wave in the metal is 250 hertz. What's the frequency of sound wave in there? 250 hertz. Frequency does not change when you go from one medium to the other. The way the speed changes is by changing the wavelength. All right, so now determine the wavelength of the wave in air. Well, velocity of a wave is equal to wavelength times frequency. We know the frequency is 250 hertz, and the way the speed changes when you go from the metal to the air is due to the wavelength, not the frequency. So we solve for wavelength is going to be v divided by f. That's 340. They gave us the speed of sound in air to use in this problem. Divided by 250, they gave us the frequency is 1.4 meters. Part D, the speed or the sound wave in air in C enters a pipe and that's open at both ends. The diagram shows the displacement at a particular time t of the standing wave that is set up on the pipe. On the diagram at time t, label with the letter C a point in the pipe that is at the center of a compression. So that would be right here. Why? Well, so being above this dotted line means that you have stuff that's displaced to the right. Being below the dotted line means you have stuff, not stuff, air molecules. They're displaced to the left. Being on the dotted line means you are at equilibrium. You haven't been displaced. Well, if you're right there at that point C, the points to the left of you are being displaced to the right. That means they're getting closer to you. They're crowding into you. Also, the points to the right of you have been displaced to the left. That means they're also being crowded into you. So you're being crowded into on both sides. That must mean you are at the center of a compression. This one right here, what would this one be like? Well, the points to the right are being moved to the right. Ooh, that means they're getting further away from you, doesn't it? Farther away from you, rather. And the points to the left of you are being moved to the left. That means also they're getting farther away from you. So here you'd be at the center of a rarefaction. So I put a point there in the scoring guide. They made it like a vertical band. I guess that makes sense because it would be true for air particles every spot. I don't think it matters either way. If you did a point or a band, what they're looking for is it's there. All right, number 4. So 3 identical light bulbs, X, Y, and Z, each of resistance 4 are connected. Okay, we got a switch. The switch S is initially open. Calculate the power dissipated in the circuit. Okay, well, power is equal to IV. And I don't immediately know the current. I could figure out the current, but I would rather just use a different equation for power because we know V equals IR. Therefore, I equals V over R. So if I just substitute V over R for I get V squared over R. So that's another equation for power. There are 3 equations for power. The other one would just be to substitute IR, and for V we get then I squared times R. But in this case, I know the V squared, and I can figure out the total resistance real quick and easy. So V is 12. 12 squared divided by 8 for the resistance because this is not in play. Switch is open. Only these two, they're in series. Therefore, we just add up the resistances. Each one is 4. 4 plus 4 is 8. 12 squared divided by 8 is 18 watts. Part B, the switch is now closed. State without calculation why the current in the cell will increase. Well, when we close that switch, now we have a parallel circuit. A parallel circuit gives more options for electron flow, which causes the total resistance of the circuit to decrease. Well, if the total resistance of the circuit decreases by V equals IR, if that decreases, then that must increase because the voltage is not going to change. It's still 12 volts. Therefore, we have a higher current. I think they may have given you a couple other ways to answer that one in the scoring guide. What they say? Current through YZ is unchanged, and then there's going to be an additional current flow through X. Yeah, that's another way you could do it. So current is going to flow that way, and this current's unchanged, right? Because these two are in parallel. When I close the switch, these guys don't even know that this one has been closed. They are unaware. All that happens is more power is pulled out of the battery. Nothing changes about this branch when this branch is put into play. We could add another branch, nothing would change about this branch. We could add another branch, nothing would change about this branch. So the current through here stays the same, but now there's going to be current going through there. That must mean there's more current coming out of the battery. That would work too. Deduce the ratio of power dissipated in Y with the switch open to power dissipated in Y with the switch closed. Now, you may be able to tell that I had stuff written that's erased because I initially thought this was power dissipated in the entire circuit. Right, that's usually what the question is, but they just asked about power dissipated in Y, in resistor Y. So make sure you read every single symbol before you jump ahead and start doing things. Well, again, just as I described here, nothing is going to change about what's going on in Y. So current through Y, and therefore the change of voltage over Y do not change. So the ratio is just 1. Y doesn't know that the switch has been closed. It doesn't affect anything. So nothing's changed. If you got 5 over 5, that's 1. 18 over 18, that's 1. Doesn't matter. 1. In fact, actually, it would be 9 watts because each of these would do have half the power output. So 18 watts would be 9 watts and then 9 watts. That's a ratio of 1. Number 5, getting to the end. A proton. A proton moves along a circular path in a region of uniform magnetic field. The magnetic field is directed into the plane of the page. Label with arrows on the diagram the magnetic force on the proton. Okay, so, well, it's going in a circle, so the magnetic force must be toward the center. And so the magnetic force is going to be a centripetal force, so it's toward the center. And I didn't call it F sub B or F sub C or anything because it just said F. So that's what it did. Now the velocity of the proton. Now I have to figure out, does the proton go counterclockwise or clockwise? To do that, I would use the right-hand rule. So the magnetic force is equal to QVB sine of theta. And I think that is in your data book. Let's see. Should be. Yep, QVB sine theta. Now, I'm going to put my fingers in the direction. I'm going to choose a direction for V and see if it works out. I know my force has to be toward the center of the circle. So I'm going to choose counterclockwise because it works best with the angle of my hand and the circle. So fingers in the direction of the current, which is the direction of positive charge flow. Cross my fingers in the direction of the magnetic field into the page, and then my thumb should go in the direction of the force. Hey, that works. And this is a proton, so that means it obeys the rule. Now, if I did this and it worked and it was an electron, I would know it's going the opposite way because there'd be a negative on that Q, so it changed the direction. But no, this works. Now, if it went the opposite way, I would go like that, cross that way, and then my thumb is pointing out. That's not the right way. So the velocity must be such that this thing's going counterclockwise. That means the velocity at this instant is a tangent, right? The velocity is always, at any instant, the velocity is tangent to the circle. Right angle with the force. Speed of the proton is 2.6 times 10 to the 6 meters per second. It's very fast. And the magnetic field strength is 0.042 Tesla. For this proton, determine in M the radius of the circular path. Give your answer to an appropriate number of significant figures. Very scary. Okay, so in this case, the centrifugal force is our magnetic force. Centrifugal force is mv squared over r. Magnetic force is qvb. Why did I not have the sine theta? Well, because the magnetic field and the velocity are at right angles to each other. So sine of 90 degrees is 1. I don't need the sine. This velocity cancels out with one of those velocities. I want to solve for r. So to solve for r, I do a little bit of algebra, divide the q, divide the b, and multiply the r up to the other side. I get r is equal to mv divided by qb. Then in your data booklet, if you don't remember the mass of a proton, right, because this mass is the mass of a proton, it's given to you. Mass of proton, 1.673. Usually we just do 1.67, but they give us that third decimal. specifically because they want to be able to show us that the mass of a proton and a neutron are slightly different, with the neutron being slightly more massive. So they give us a mass of a proton. Excellent. Times the velocity. They gave us the velocity. Q, the charge of a proton. Well, that's just the elementary charge. If you forgot the elementary charge, there it is, right there. 1.60 times 10 to the negative 19. So 1.60 times 10 to the negative 19. And then times the magnetic field strength. They gave that to us, and you get 0.54 meters. Is the radius of the circle. Number 6. Deuterium, which is a hydrogen with a neutron, or a proton and a neutron stuck together, undergoes a fusion according to the following reaction. A deuterium plus another deuterium leaves us with a tritium plus something. Identify the particle X. Okay, well, we had one proton, another proton, then we only have one proton. The other thing must be a proton. So it's a proton. Or you can say H11, because that's a hydrogen nucleus. Or you can say proton, or you can write out the word proton. Okay, the following data are available for the binding energies per nucleon. Determine in mega electron volts the energy released by this fusion. Okay, so I just do the energy for this tritium minus the energy for these guys, and then I'm done. Wait a second, let me just check something real quick. Yeah. Okay, so yeah, I just do the binding energy for this, and this is per nucleon, so I do 3 times the binding energy for that tritium, minus the binding energies I started off with here, and I had 2 of them, and there are 2 nucleons, so that's why I multiply by 2. So I do my 1.12 times 2, and then I had 2 of them, so I'm going to multiply by 2 again. So that's really multiplying by 4, and I'm left with 3.86 mega electron volts. Done. Okay, wait, just let me check something real quick again. Okay, I was just looking at the scoring guide because there was something weird in the scoring guide. But it's exactly what I did here. It's just they presented it strangely. Okay, suggest why for the fusion reaction above to take place, the temperature of deuterium must be very high. Well, these are both positively charged. That means they're going to want to repel each other by Coulomb repulsion, by by the Coulomb force. Now, they need to get really close for the strong force to take over and snap them into place so you can get your fusion. But how are you going to get them really close if they really want to repel each other? By moving really, really fast. Well, if they're moving really, really fast, so they can get close enough to overcome the Coulomb repulsion and get into the range at which a strong force applies, they better have a whole lot of energy, which means that they have a whole lot, or they have a very high temperature. So you need a high kinetic energy to overcome the Coulomb repulsion between deuterium particles, and in order to achieve a high kinetic energy, you need a high temperature. Particle Y is produced in the collision of a proton with a K- meson in the following reaction. Okay. The core content of some of the particles involved is the K- is anti-up strange, and the K null or K0 meson is down anti-strange. Okay, so identify the particle Y. So what's the particle Y going to be? What I did is I identify for the particle. They didn't tell us to identify the particle. I'm sorry. They just want us to identify the charge and the strangeness. Okay. So, well, this has a charge of a negative charge, hence the negative. This is a positive charge. It's a proton. This has no charge, hence the 0. This is a positive charge, hence the plus. Now, if we're going to conserve charge, and we must, then that's 0 net charge. This must be 0 net charge. So this thing must have a charge of negative. So -1. Or you could just say negative. Or I guess, I don't think you could just say negative. You could say negative E, though, right? Because when I say positive and negative, those are all the elementary charges. I also wrote out the quark contents, or the quark makeup of each of these particles. So the K minus is anti-up strange, plus a proton is up down, goes to this K0 is a down anti-strange. If you do the charges for that, you're going to find it is 0. A down has a charge of -1/3, and a regular strange has a charge of -1/3, but an anti-strange would have a charge of positive 1/3. So -1/3 and positive 1/3 is 0 charge. That's why it's 0. And then our K minus, they did tell us a K minus. Wait a second. Yeah. Oh, it's a K plus, I'm sorry. Now, K plus is the same as a K minus, except you change where the antiparticle is. So instead of being an anti-up strange, it's an up anti-strange. And this would have a charge of -1. I'm sorry, +1. This one has a charge of -1. This would have a charge of +1, because this is positive 2/3. A normal strange is -1/3, but this is an anti-strange, so it's +1/3. 2/3 plus 1/3 is +1. And then left over here, whatever is going to be there. Now, we also want to identify the strangeness for this particle. So that's what I was doing here. The strangeness here is -1. A strange quark has a strangeness of -1. Here, there's no strange quark, so there's no strangeness. This has a strangeness of +1 because it's an anti-strange quark. This has a strangeness of +1 because it's an anti-strange quark. So here, I need to have -1 is equal to -1 in order to conserve strangeness. Well, what must the strangeness of this thing be to do that? It must be -3 strangeness. So this must be a strange. And there we go. And -3 to conserve strangeness. You didn't have to write to conserve strangeness. And you might say, but wait a second. If it's a weak interaction, the strangeness need not be conserved. That's true. This is not a weak interaction. I know that because it's produced by collision. Weak interactions are spontaneous. This was an interaction due to a collision. So strangeness must be conserved in this case because it's not a weak interaction. Last problem. The average temperature of the ocean is that oceans behave as black bodies. Show that the intensity radiated by the ocean is about 400 watts per square meter. Okay, well, intensity is equal to power divided by area, as you get in your data booklet for topic 8. Topic 8 down there. We've got power, and then we've got intensity is power divided by area. Now you might say, my power does not have an E in it. Well, E for a black body is 1. This is the emissivity constant. For a black body, it's 1. So I don't need it. And we talked about this in the astrophysics unit as well. So then the area cancels out, which is a good thing because we don't know anything about that. And then you just have that intensity is the Stefan-Boltzmann constant times temperature to the 4th power. And they gave us a temperature. So we just plug in the Stefan-Boltzmann constant. It's in the list of constants in your data booklet. Times 49 to the power 4. Use a calculator. And then you get we get 396, which is approximately 400 watts per square meter. And then lastly, explain why some of this radiation is returned to the oceans from the atmosphere. Well, so you're radiating out 400 watts per square meter. And at this temperature, most of that is infrared radiation. Now, in the atmosphere, we've got greenhouse gases which absorb and re-emit infrared radiation. When they emit that infrared radiation, they scatter it randomly, which means some of it is going to scatter back down to the ocean. So there you go. Now, the points for this, let's see what exactly the points were for, because 3 points means probably 3 things to say. Let's see. Most of the radiation emitted by the ocean is infrared, or just infrared. I did IR there because I realized I was kind of taking for granted that it was IR once I started writing, and then I didn't have much space, so I just put IR there for infrared. This radiation is absorbed by greenhouse gases in the atmosphere. The greenhouse gases re-radiate or re-emit this infrared radiation. That's a 3rd point. And then the fourth point is partly back toward the ocean or in all directions that radiation and other awareness that radiation in other directions is also present. So that was 4 things they just gave us. If you hit 3 of them, you get all 3 points. And that is that. The May 2019 version 1 of paper 2. Have a nice day.